Okay, hello everybody. My name is David Fernando Porlles Lopez. I am currently pursuing a PhD at PUC-Rio, and in this video I will present this work titled Quantum Geometry of Singlet Superconductors. Okay, the outline of my presentation is the following. First, the introduction, where I will talk about the motivation and the main goals. After the quantum geometry of SY superconductor, where we will see the definition of a quantum metric, the fidelity number, and fidelity marker. Later, we will explore some electromagnetic response of the single superconductor and in how we can relate this response to the quantum geometry properties. Later, we will see the quantum geometry of the wave superconductors, and finally, the conclusion and perspective. Okay, for the motivation, in recent years has been emerged several studies that talk about the relationship between the quantum metric and electromagnetic response and different material, for example, semiconductors. And also superfluidity has been appears the relationship between quantum metric and superfluidity with flat bands. This work and other similar studies has prompted us to study how is the quantum metric in superconductors. In this case, we will study for single superconductors, where our primary objective are to determine whether the quantum geometry properties are trivial or not in these single superconductors, and explore the possibility to optically detecting these quantum geometry properties. Okay, now for single superconductors, we have this Hamiltonian, where we can express as dk and the sigma, where dk is the part that depends of k and sigma are the Pauli matrices. In this case, this component D1 is the superconducting gap, and D3 is the energy dispersion in the normal states. And if we diagonalize this Hamiltonian, we obtain two bands with this energy, where we have the field quasi-Hall eigenstates and the anti-quasi-particle eigenstates. In our case, in our work, we will focus on this eigenstate, the field quasi-Hall eigenstates, where we can see that obviously that depends of D1 and D3, but also we can express this eigenstate as a function of this unit vector that depend on the Bogoliub's coefficient. This unit vector we will import later to visualize the quantum metric, but we will see that later. Okay, now that quantum metric of single superconductor, but what is the quantum metric? Well, where it comes out? First, if you have a state C of k and you overlap this state with itself at a slightly different momentum, and you take the modulus and you do an expansion, we will appear this prefactor here. This prefactor is the quantum metric. Okay, another way to visualize this is if you have a unit vector defined in k and you rotate, you go to k plus delta k, this unit vector will rotate. And if you take a product, this product will be less than 1. And that correction will give us again this quantum metric. Okay, as we have seen previously, the Hamiltonian of the single superconductor has this form, and we can define a unit vector using this v of k. And for single superconductor, we have this expression for the quantum metric for the quasi-Hall eigenstate. And after some calculation, we can obtain this form equivalent to this quantum metric, and where it depends of D1 and D3. Okay, now using this formula for the S-wave superconductor, we obtain this simple form of the quantum metric, where it depends on the gap, superconducting gap, This term that there are the Fermi velocity and this energy dispersion of the superconducting states. Now, also we define this unit vector, as I said previously, for the field quasi-Holland state. We define this unit vector using the Porlles coefficient because we will help us to visualize the quantum metric, and we will see that now. Okay, we have to figure it here. This figure on the left is the vector field of this unit vector, and this other one is the density plot of the value of the quantum metric, both on the momentum space. And this dashed line is the Fermi surface. And we can see that the quantum metric is very large near the Fermi surface. That is because below the Fermi surface, the Einstein state is more like a electron-like. Above is more hole-like. So near the Fermi surface, because of this change, the quantum metric is very large. And we can visualize this in this figure where this unit vector will change its direction very quickly near the Fermi surface. And we can say that the quantum metric is just the twisting of this vector field. So we show a way to visualize this quantum metric. Okay, now let's go to another property. This property is the fidelity number. And this is the quantum metric integrated over the Brilliant Sun. And physically, that represent the average distance between neighboring quasi-Hall states in the Brilliant Sun. That is very important because in our work, we demonstrate that this fidelity number is expressed in terms of the coherent factors. So we can say that if we have some properties that is a function of the fidelity number, these properties can also be expressed in terms of that coherent factors. And also, we obtain another conclusion, that is that a coherent factor can be understood as an average distance between the neighboring quasi-Hall states. That's very important. Okay, now let's go to the fidelity marker. This term represents the map of the fidelity number in real space, and the formula for this property is the following, where this P and Q represent the projectors in real space, and R mu and R nu represent the position operators. And this is very important because we can see the effect of disorder in the quantum geometrical properties. So here we have the center region of a lattice, where this sphere here, the volume of this sphere represent the value of the fidelity marker. And in each case, we consider a different non-magnetic impurity at the center. And we can see that this magnetic impurity decrease the value of the fidelity marker locally. And we can say that non-magnetic impurity reduce the average distance between the quasi-Hall state in the momentum space. So the disorder affects the quantum geometrical properties. Okay, now let's go to the electromagnetic response. If we consider a singlet superconductor subject to electromagnetic wave, we can study among different electromagnetic response. In our work, we focus on the infrared absorption, the paramagnetic current, and the static dielectric function. For the infrared absorption, if we consider this vector potential, we can study the infrared absorption through the real part of the conductivity, that it is expressed in terms of the imaginary part of the current correlation divided by the frequency. And in the case of paramagnetic current, if we consider this vector potential, the London equation, the current will be modified in this way, where this one is the diamagnetic current that is related to the Meissner effect, and this other one is the paramagnetic current. That so named because it cancels out the magnetic current. And we can express this term here as a response times the vector potential. Okay, in the case of the static dielectric function, consider the frequency, and using the RPM random phase approximation, we can have this equation for this dielectric function, where Bk is the Fourier transform of the Rio potential, and this term here is the susceptibility. Now, in our work, we focus on study or calculate these terms. And to do that, we use the polarization operator. And after solve calculation using the linear response theory and also the Matsubara formalism, we have this expression for each electromagnetic response, when we see that appears this term here that depends on the Bogolius coefficient. This term will are the coherent factors. And we ask ourselves, can we establish a relationship between this coherent factor and the quantum metric? And to answer that, we will see that we will do some approximation. First, the coherent factor are the following for each electromagnetic response. And consider that for S-wave superconductor, the gap is of the order of 0.01 electron volts. We can do an approximation because this wave vector of the light is much smaller than the energy, the Fermi momentum. That is because of this wave vector. The value of the wave vector that we need to excite the quasi-particle is much smaller than this Fermi momentum. So if we do an approximation of the wave vector, we obtain this expression, and this term here will be canceled out in the integration. And we can see that from these two expressions, we can obtain the quantum metric times the wave vector squared. In this case, will appear another terms, but the important part here is that appear these quantum metrics times this wave vector. Now, if we replace this in our previously equation, we obtain this final equation for this electromagnetic response, where we can see that for the infrared absorption, we obtain the integration of this term here in unit correct and times the quantum metric, and for the other one, we obtain the fidelity number. So through this equation, we establish a way to optically detect the quantum geometrical properties. And that was one of our goals. Now for the quantum geometry of D-wave superconductors, we have this expression for the gap superconductors, where we can see that appears nodal points, and the quantum metric for this kind of superconductor is given by this expression, a more complex expression, and we define again this unit vector here, and doing the same as we do for S-wave superconductor, we obtain this figurate where we can see that in the nodal points appears a very singular behavior of the quantum metric. And in this point here, the quantum metric diverge. And we can visualize this using this vector field because in this part, we can see that it forms a vortex. This vector change its direction very dramatically. And after that, we also studied the fidelity number, and we can see that the fidelity number diverge because the singular behavior of the quantum metric. So for this kind of superconductor, D-wave superconductor, we can't establish a relationship between these quantum geometrical properties and the electromagnetic response because the singular behavior of this quantum metric. Okay, now the conclusions and perspective. First, we have shown that the properties of quantum geometry, the quantum geometry are not trivial for both S-wave and D-wave superconductors. Second, the quantum geometry properties are influenced by disorder in S-wave superconductors, as we see for the fidelity marker, using the fidelity marker and a non-magnetic impurity. Also, we have demonstrated that the possibility of optically detecting these quantum geometry properties, as I showed you previously, and that was one of our goals. And for future research, other types of superconductors with different pairing symmetries could be considered, such as the case of triplet superconductors. Okay, that's all. If you have if you want more information about this work, we have a paper related to this work titled Quantum Geometry of Singlet Superconductor, and you can find it in the description. Thank you very much, and subscribe to the channel.